All right, guys. So this was actually a very quick test because I wanted to make sure that we actually do speak English, right? I mean, I have had this experience before. Like after 3 lectures, somebody comes and says, like, "Well, I'm sorry, I just actually don't speak English." I'm like, "Okay, well, what are you guys doing here then?" Anyway, so it's going to be in English. Feel free to ask questions. Again, if by whatever reason you misunderstand things, it's okay to switch to Russian. I will then try to translate into English, but let's try to keep it in English, okay? All right, so with this introduction, let's get started. So the lecture today is Introduction to Network Science, and in fact, the network science as a science is a very, very young science. So like the first paper that talked about networks that became kind of well known and well cited goes back to 1998. So it's pretty much 20-year-old kind of science, right? And before, people talked about complex networks. People talked about, they call this the field of study, graphs networks, et cetera, with sort of rise of data science, right? The network community decided also to join this trend and called themselves like network science, right? In fact, this is really part of, if you think about like bigger picture, yeah, it is a part of data science simply because, networks is about connection and about interaction, right? And so, sometimes you see physical networks, but very often you work with sort of virtual networks where connections is just about interactions, right? Think about friendship network. That's why, that's why a lot of methods and techniques that we're gonna use in network science, they're also used across data science. And in some sense, I would say, this course is actually a good sort of complement to general machine learning and data mining courses. And the difference, again, here it's all about connections. When you talk about machine learning, you usually talk about like independent samples and predictions. Here, it is more about connections and structure. And in the second part of the course, we'll actually merge what we learn now with machine learning. All right. So the course trivia, right? The details. So I'm gonna be doing lectures. We'll have 2 instructors, Ilya Andreevich Makarov and Laurent Baudou, who will be doing seminars. And the course is 2 modules. We'll have 10 lectures, 10 seminars each module, but we're gonna group them. So it's gonna be 5 days overall, right? So we'll have lectures on Saturdays every other week. We'll have seminars, labs on Tuesday every other week. Okay? Now, there is a website for this class. That's the address, and I'll put there all the lecture notes, and so the slides will be there. And also, if you go through change 2019 for 2018 or 2017, 16, 15, 14, 13, 12, you'll get all this, course from the previous years. And there are also some of them are actually videotaped. And also on the site, you will have some papers, so you can, click and download. Emails, here, programming, we're going to be using Python, Anaconda, IPython notebooks. Are you familiar with, yeah? Okay, good. So we're going to go into more details about the programming during the seminars and labs. Now, libraries, we're going to work around this Network X library, mostly. And for visualization purposes, there are a couple of visualization tools that we're going to use, right? So the course, though, we're going to do a lot of, I'll do, of course, talking and theory, but there is a pretty big emphasis on practical exercises. And in terms of controls, we're going to have, written control work or exam at the end of this module, and then there's a big exam at the end of the second module. During this module, we'll have homeworks and labs, and the next module, it will be more of sort of project work, right? That will require you to analyze real networks, okay? So that's sort of the plan. Prerequisites for this course. So I expect you to know a bit of discrete mathematics, linear algebra, a little bit algorithm data structures, a little bit of probability theory, differential equations here and there, and programming. Does anybody have any problems with these prerequisites? Okay, what? Differential equations. Differential equations missing. Okay, anything else? Differential, okay, nobody likes differential equations. That's fine. We're going to actually talk about them in the second module a little bit, not that much, right? So it's going to be probably one lecture, so you don't really need that much of a background. But the rest is quite important, especially like linear algebra and the whole story about like networks, graph, discrete math. And of course, I'm sure you're fluent in Python, right? Sort of? Kind of? Okay. All right. Textbooks. You guys lucky now there is a very, very nice textbook. And I actually have even like a real book here. This is a book. The good news, it's actually also completely, the entire book is available online, in PDF, and it's just also version for the website. The guy, Albert Laszlo Barabashi, he is a physicist. He is from Boston Northeastern University. He is actually a very famous guy. He is one of the people who started this whole network science. And the book is actually very cool. So I strongly recommend. There are a couple other books. One is called Networks: An Introduction by Mark Newman. He's a physicist. That book is actually a little bit more, math heavier than this one. Then there is this classical book on social network analysis by Stanley Wasserman and Catherine Faust. That's where the whole thing started within social sciences. And then there is actually a pretty cool book, Networks, Crowd, and Markets, and it's also available online. This is from John Kleinberg, theoretical computer scientist, and David Easley, who is economist from Cornell University. Very, very interesting book, less mathematical, but actually very, very interesting connection between network science and economics. All right. So overall, the first book, this is a must, right? This is the reading that will be required. The rest of the books, this is just for your, information. I will also provide at the end of every lecture, I'll also provide you with a list of research papers where the topic has been discussed, right? And most of those papers goes to late 90s, early 2000. When this sort of field starting to be established. I created that list before the book before the book was available. But right now, again, this book pretty much has its all. Topics, what we're going to do. Overall, within these two modules, we're going to cover, first topic will be statistical properties of networks. And we're going to talk about, overall what networks are, and how you can characterize them, what kind of statistics you can use, big picture. Then we're going to dive into actual structure and the connectivity patterns and the dynamics of the networks, how things grow, how things change, evolve. We're going to talk about processes on the networks, and that is like epidemics or rumor spreading. So things where you have a network as a background, and then something happens on top of it. For example, how likes propagates in Facebook, right? And then we're going to talk about network embeddings. This is a sort of a new topic within network science where people look at how you can actually take this sort of network and assign coordinates to every node in the network and embed it in a certain space of some dimensions, such a way that it will show you more of internal sort of latent structure in the network. For example, similar nodes will end up next to each other in this embedding. Think about projecting, this very complicated network on 2 dimensions, right? If you do this, this is just graph drawing. But you can actually, to draw a graph, you need to assign coordinates to every node. And so how to do it in a smart way, that's what network embeddings are about. And also the difference is you embed not necessarily in 2 dimensions, but in multiple dimensions. And finally, we'll spend several lectures on prediction on networks. And that's really machine learning application to networks, where we talk about predicting the properties of the networks. Let's say, we know something about your friends. What can we infer about you? Say, age, your income, location, etc. And also prediction of edges. And that's what's, for example, used right now by Facebook, LinkedIn, and other social networks to recommend your friends, right? Or sort of people you might know. So the links that sort of missing in the network, but that could be there, right? And then we'll also talk a little bit about sort of dynamic and evolution within the networks. So that's overall topics. Any questions so far? Do I speak too slow, too fast? Do you understand me? Okay, good. All right. So this module, this 10 lectures, we start with introduction of network science, and that's what we're actually doing right now. And the rest of the lecture will be like about introducing network science. We're going to talk about power law and scale-free networks today. Next couple lectures is going to be about random graphs and small world and dynamical growth models. We're going to talk more about what that is. We then go lecture 5 and lecture 6. This is about structure of the networks, and we're going to discuss what's called centrality measures, the importance of every node within the network, and talk about the famous PageRank algorithm and how it's used to determine the importance and the influence of every node in the network. Then we're going to dive in more into structure of the networks and talk about what it means for nodes to be similar on the networks in terms of their connectivity patterns. We talk about what's called network cores and community structure. And community is a sort of group of nodes that are more connected to each other than to the rest of the network. And then we'll spend 2 more lectures on graph partitioning algorithms, and that's a way to split the graph into pieces or network, and community detection algorithms. Okay? So that's the plan for this module. All right. Shall we get started? All right, let's do it. So, as I mentioned before, network science is actually very, very young science as a science, right? It's 20 years old. And next time I'll try to bring this paper written for this 20-year anniversary, and also sort of the paper that started this whole thing. But in general, people talked about networks for a long time. And if you think about sociologists, they studied, of course, human interaction and social networks, and that's where the name came from, back in like 30s and 40s. Though in those days, the study was, okay, let's look at the group of people, right? Let's just put out questionnaire, let's see who is friends with whom. So it was on a very, very small scale, right? And it's only back into, say, late 70s, 80s, when the scale started increasing. Then, of course, mathematics. Well, people, mathematicians in math talked about graphs as objects for a long time, right? It goes back to, 18th century, that's sort of the fundamental graph theory. And that's kind of gives us mathematical background to networks. There was a lot of interest from mathematicians in graph theory in mid 1950s, where they discovered properties of what's so-called random graphs, and that created a big push and a lot of interest. It was a famous mathematician, Paul Erdős, who worked on that. So that's sort of another kind of background that comes into network science. Then, of course, computer science. They talked a lot about graphs, and I'm sure you're familiar with like breadth first search, depth first search. I mean, all those algorithms on graphs that you use today. That's where things coming from. Now, interestingly enough, the biggest push in creation of this network science came from physics and from statistical physics. And the reason for that is because there was a sort of part of physicists and that were working on the topic of complexity. A very interesting topic, complexity in the system, what actually means for the system to be complex. And part of them we're looking at actually at also connectivity patterns, because the system is complex when there is a very complicated interaction, and when you sort of, you zoom in and the system looks pretty much almost the same as a big picture. Think about like fractals. Do you know what fractal is? Right? Sort of self-replicating object. And those guys start looking into networks, and actually Albert Laszlo Barbashi is one of those physicists, Mark Newman another of those physicists. There are many more names who actually start looking into connectivity patterns and really push this network science. Though they were talking back then about complex networks. But now again, it's all kind of an umbrella of network science. Then of course economists. There are a lot of sort of interest in economics in network science, and now here you're talking about, I don't know, money flows, money transfers, you're talking about transportation networks, pretty much anything that deals with economics. And there is a lot of interest today from bioinformaticians, right, bioinformatics, where we talk about sort of interaction in proteins or sort of interaction between drugs, et cetera, et cetera, et cetera. So these are all sort of subfields of real big science that contributes to network science. Now, because of this, network science is kind of very, very versatile. In fact, each of those subfields have their own scientific journals, scientific publications, their own jargon, their own sort of ways to talk about things. And what you will see sometimes that the same phenomena has different names depending on who is talking about it. And that even starts from like sort of very, very simple definitions. And as always, sort of mathematicians becoming the strictest guys, right? Physicists like to talk about like spherical cows, the sort of the big ideas. Economists, bioinformaticians, it's more about application of stuff. Sociologists, they talk about, actors and interaction and, how things, how people feel, et cetera, et cetera. You will see these differences. Today, there are obviously all the conferences that existed in each subfield, still exist. Each of those are huge fields of science. But then there are some conferences where pure network scientists come and talk about sort of network properties. And of course, the idea was that it doesn't matter where the networks come from. They have some sort of unique general properties, right? And if you learn them, in one field, you can actually use them. You can use those properties for the networks from other fields, right? And that's sort of the greatest idea, for example, for physicists, that there should be some universal law, like gravitational law, right? And based on that law, networks being created, and then whatever subfield of science you take, you know how to describe the networks. It's not exactly that way. But interestingly enough, 10 years ago, scientists believed that, yes, all networks all networks are pretty much equal, right? So if you learned one, you kind of learned all of them. Not exactly true in real life. We're going to look into this. So speaking, if some of you are interested in actual sort of science, right, and taking this course for like sort of science sake, and you think about maybe, going to grad school or, getting PhDs, then I strongly recommend you, and this topic or think about like writing a diploma based on this topic, I strongly recommend you to look into some journals to see what's sort of the latest and greatest happening within this science. So the top 5 journals, this is pretty much where you need to look at. And what's interesting, notice the dates there, that's when the journals has been started, right? If you think about physical review letters or physical review, I think it started like in mid or early 19th century. If you think about Nature as a magazine, right, or Science, that goes back probably to like 19th century. Now, this journal started like 2, 3, 4 years ago, and that's when the network science community became big enough to support a lot of publications and have like lots of research. And there are many more journals sort of around this, but as always, there's like sort of different quality of journals. Again, if you're interested, just check what's happening within the field. And as I mentioned, a bunch of conferences, different flavors. Again, there is like, for example, very much on sort of pure network science, which is this NetSci conference or International Workshop on Complex Networks. But then the SciAm workshop, this is more of mathematicians. Computational social science, well, speaks for itself. It's for social sciences. Social network analysis, obviously social sciences. StatPhys, that's physicists. ACM, that's computer scientists. So there is still sort of conferences driven by different sciences, and depending on sort of what, in some sense, you like more, right, or what's driving you. If you're a social scientist, it's maybe like social science conference that's more of interest. If you're physicist, physics conferences, et cetera, et cetera. But anyway, just wanted to show you that there is like a lot of activity, and though this is a very young science, there are a lot of people involved into actually building it out and working on things. Okay? So, as I mentioned, because the science has been sort of blended from different subfields, very, very different subfields, there are also quite often even different names used as a sort of fundamental terminology. Like, as I mentioned before, and you probably heard already, I'm talking about networks and graphs, right? So there's actually no difference. Network is a graph, right? Or network, which is connection, it's represented by a graph. So it's the same. Quite often we say nodes or vertices. It's also the same. If you look at the literature that comes from social sciences, people talk about actors. Now, we also say in a graph, we talk about links connecting the nodes or edges. It's also the same. Social science literature will talk about relations. Then there is, quite often, there is a sort of mixture. I mentioned the word communities or groups of nodes that are closely connected to each other. Quite often people talk about clusters on the network, on the graphs. That's also meaning communities. So you will see like a lot of this terminology that is not sort of exactly the same, but has the same meaning. How many of you remember anything from like fundamental discrete math or graph theory? One shy hand. Oh, come on, people. When did you have the graph theory class or discrete math? A couple of years ago? Last month. All right. Okay. Then we go very quickly through this. Like I have like 3 or 4 very boring slides, but this is sort of for those who actually never had graph theory. That's sort of the mass notation, right? So network represented by graph, and graph is a set of vertices and edges connecting this, right? Now, very importantly, graph can be represented through a matrix, what's called adjacency matrix, where it's a square matrix, and if there is a connection between 2 nodes, the matrix where the one node corresponds to the row and another node corresponds to the column has a non-zero value in that cell. And if the graph is unweighted, then the connectivity pattern represented by a binary 0-1 matrix. So it's 0-1, 0 in the matrix if there is no connection between the corresponding nodes, and 1 if it is. And if it's a weighted graph, which means you have a weight on an edge, then matrix is non-binary. Graphs can be directed or undirected, right? Directed is there is preferred direction from one node to another. Undirected if there is no. And in terms of matrix, if the graph is undirected, the matrix is symmetric. Now, with this whole directed, undirected graph thing, it's actually quite important to understand and to notice the difference when we use this in different, well, we don't do theorems, but when we calculate different properties. The reason is because the fact that there is a directionality in the graph can change its properties dramatically. Think about Moscow, when you could drive both ways, right? When there is 2-way streets versus what they did a lot right now in downtown, the center of Moscow, 1-way streets. Right? All of a sudden, getting from point A to point B, it was easier, but now it might take you 2 minutes to walk. It might take you like 35 minutes to drive because it's a 1-way street, right? And you're thinking like, what the hell they were thinking? Actually, in fact, Moscow is the worst city in the world in terms of this extra distances. There is a metric that compares your direct distance versus how much you actually have to travel, right? And this ratio is insane for Moscow. So, and that sort of directed, undirected graph makes huge difference. Okay, and I mentioned what directed graph is. Now, we'll be talking about like this shortest path idea. Now, what's the shortest path? Come on, somebody who remembers network, who remembers, yeah. Okay, yeah. It's a geodesic distance, right? A number of the smallest path between 2 vertices, right? The shortest path, obviously. Good question. If it's unweighted graph, we do not. If weighted, it depends on. We can either talk about weighted shortest path and then you put in weight. We talk about the diameter of a network, right? We talk about the diameter, which is the longest shortest path, which is you have a network and you measure the distance between any 2 nodes and you find out the largest. Now, this is actually quite tricky metric. you think, I mean, you do all these metrics to understand some properties of the networks, right? Now, think about this. Why network diameter is not a very good metric for a graph? I mean, it's important, right? Because you need to know, how long it takes you, right? You think about, for your diameter, it's probably the size of the graph, right? In some sense. How many steps it takes to get from one point to another. But I'm saying that, yeah, it's an interesting metric, but in practice, you actually want to avoid it. Why? Okay, so there is a computational challenge. It's n squared computation, not a good job, right? I mean, not a good thing to do, but that's not the reason. That's the point. Think about this. Think about a graph, right? Like very compact, very well connected nodes. And then there is a long, long chain of nodes, right? This node connected only to this only to this to this, to this, to this, to this. Okay? Right? So something in a long, long tail. Now, if you think about diameter, it's actually will be determined by this long, long tail, right? But in fact, graph is very compact. It's just this tail hanging out. And so if you calculate diameter, it will tell you, oh, I don't know, 20, 30, 50. But in fact, most of the nodes are on average, the distance is much smaller, right? And so the good metric, the stable metric we usually think about is the average path length, which is, you calculate all the path lengths, but instead of like taking the maximum, you're taking average. Now, you're absolutely correct that with large graphs, it's actually computationally almost impossible to do. But the good news, when you do average, what you do is you just take a few samples, right? And that solves the problem. So instead of actually computing all the shortest path, you just randomly pick up nodes, calculate the distance, and there you go. Okay, graph is connected when there is a path in between every pair of nodes. In a connected component is a maximum subgraph where you can get from every node to every other node. And if you have a directed graph, then there is weakly connected. It's going to be weakly connected if you remove all the sort of arrows, all the directions, and then still connected. And a directed graph is called strongly connected if you can get from any node to any other node just following the arrows, right? Any questions about this? I'm going actually very fast through this, but I'm hoping you know it. If you do not, please spend some time during the week and refresh it. Now, the vertex degree, well, it's really the number of edges that is incident to the vertex. Or, if you think about social networks, it's just the number of friends. And we're going to be talking a lot about the degree of the vertex. And actually, we're going to be talking about the distribution of degrees of vertices, right? Which is how many vertices or what degrees exist in the network. Isolated vertex if there is no incoming edges. And if we have a directed graph, then there is always, of course, in degree, which is the number of edges that points to the node, and out degree. All right? And, vertex with in degree equals 0 is called the source vertex. So think about the source. So there's sort of the edges emanating from it, but nothing comes in. And of course, if out degree is 0, then it is sink vertex. So everything comes in, but there is no way out. Okay? All right. Anything else? I think we're done with sort of very simple definition. What I described, this definition will be enough for us for probably 2-3 lectures. Then I might spend a little bit more time on sort of discrete math. If we need it. Okay? But now we know what we're talking about, right? We know what graph is, we know what vertices are, we know how to find the shortest path. So now let's switch to actual sort of networks. And remember the story of physicists. And if you look on the right, this is sort of typical example of complex network, right? And that's what physicists had been looking at, back in 2000. And, the feel here is, it is obviously not regular in the sense that, it's not a grid, right? But it's also not very random, right? It looks like there is some patterns in there, right? There is sort of, partially you see the sort of, tree and leaf structure, right? like branches going out and there's a sort of leaves on them. You also see that you probably can grab a piece of this and kind of, duplicate it and it can match, other parts of the graph. Maybe you can actually zoom in, you will see very, very similar structures. There is this little bit of this fractality. There are some other interesting and unusual properties we're going to talk about in a minute, which is called the scale-free properties. And, overall topology is not trivial. Again, you cannot just describe it by saying like, oh, okay, well, I have a central node and other nodes are like sort of, on the rings around it, or it's a grid or something else, right? So you look at this, you think like, okay, well, there is some patterns. It's not obvious, right? It's clear that it's not completely random, but, we need to try to sort of capture this essence of complexity in here. And that's what the sort of network science is going to be about, trying to sort of capture those properties. I'm going to go over a few examples, and these are probably like sort of first examples when the network science just started. There was a lot of interest, and there were like a lot of publications in Nature and Science with the great visualizations. And this is, for example, back in the days, this backbone of like internet traffic routing, right? There is, traffic routes through different servers around the world. Again, this is 20-year sort of old picture, so it's not that big. Every dot here corresponds to bigger router, and connectivity is the actual, physical fiber that connects, or actually not physical. In this case, it's just routes that connects those routers. Now, it's a beautiful picture, right? It's clear that the thing is very complex, but it's also a little bit troubling because it tells you that, look, you can create a beautiful picture, but it's sort of useless, right? Because looking at it, you're like, okay, well, cool, it's abstract art, right? You can put the painting in, modern art museum, and yeah, cool. So what, right? But and that's why when you look at the big networks, just simple visualization does not help. You actually need to study properties. Now, the idea here, of course, to show you that, like, if you look around, there's like a bunch of those sort of kind of stars, right? Which is clear there is like some routers, and there are a lot of other routers connected to it, and there are some sort of connections, probably like long range. Some of them are like shorter range, but it's more of like an abstract art form. But actually a very cool picture, and this is done in 2003. This is something more meaningful. Until quite recently, you could actually grab, and I don't know why the resolution is bad. Until recently, you could quite easily grab your friends from Facebook. I'm not sure if, after all this last year troubles, I'm not sure if they still allow you to do it. Do they? No. Yeah, so there's some issues now. But back in, a few years back, you could actually grab your friends and friends of friends, and so you could actually create a sort of your small, visualize your own world, right, within the Facebook. And this is just a very simple visualization where, in fact, there are a couple things happening. Again, okay, this is a picture. Now, what we see here is a couple things. First of all, the graph, right, which is nodes and connections, it is embedded in 2 dimensions. Embedded means it's drawn in 2 dimensions. Every node got a coordinate, right? So it has x and y coordinate that allows you to plot it. Now, it's actually not just sort of randomly assigned locations, right, on a picture. It is calculated such a way that groups of nodes actually that are connected, they are also mapped or projected together next to each other, right? So that's what graph embedding is about. And such a way that you see those communities or groups. Now, in this case, the research actually labeled those communities and color-coded them, right? So there's a sort of high school friends, there is like neighbors, there is a student, then there is, husband's family, then the social media they interact with. So But the trick here is, first of all, how to map those things onto dimensions. Second is how to actually detect those communities automatically and color code them, right? And so we're going to talk about algorithms, how to do it. One other thing to notice here in this particular picture, it's egocentric picture, right? It's a picture that is where the sort of the data collection started from the particular person, right? And for other people, sort of a lot of connections being cut out, but for this person, every connection that he has is present here. And that person shown by the largest node, and the visualization trick is, of course, you know, the more connection the person has, the higher the node degree, you know, the larger the circle you use to show him, okay? I mean, it's a sort of trivial thing, but it does take a lot of algorithms to actually do this visualization. Again, you need to embed it because you need to assign coordinates to every node. You need to detect those communities to color code them. That's, you know, that takes algorithms. And for this small graph, you don't even care a lot about sort of computational properties of the algorithms, meaning if it is even n cubed, right, you're okay with this. But on larger graphs, you know, n squared doesn't work. If a graph had 1 million nodes, million squared, what is it? 10 to the 12, right? Well, it's a lot, right? And so you don't think about those algorithms. Usually n log n, or, you know, linear algorithm that actually can be used. So there are a lot of things behind this. Now, this is quite old but famous picture, and by some reason, it doesn't show me the entire slide. Give me one sec, maybe I can adjust this. I don't know. Anyway, it's actually, there is, when you get the slides, there is a reference where this picture is taken from. Anyway, so what this is a Twitter and political polarization on Twitter. That's for US, you know, not today. Again, this is back 10 years ago. Right now, it's going to be even stronger. This color-coded by, you know, Democrats versus Republicans. You know, the idea is that these are people who, two people are connected if they retweet each other, right? Or if one person retweets another person, they're connected, color-coded based on their preference. The yellow one is sort of in between. And you notice that it's called political polarization because, you know, blue guys only talk and retweet to blue guys, red only listen and talk to red guys, right? And there is a thin layer of people who kind of can actually talk in between, right? And that's very interesting from a social scientist perspective, like how society is organized and how it's polarized. In fact, this picture, there is a progression, of course, like depending on, say, US presidents. Like right now, US as a country is extremely polarized politically, right? But when Obama was a president, it was much less polarization. So you can actually observe a lot of social behavior on this type of visualizations. That's sort of yet another sort of retweets on Twitter. By the way, does anybody here use Twitter? One person, two. I mean, it's kind of interesting how things change. Like if I remember asking this question maybe, you know, 5 years ago, or like maybe 7 years ago, right? The entire classroom would be like, yes, we're on Twitter, right? Now we're all where? On Instagram? No? Facebook? Contact? What else? No? Telegram. Okay, there you go. So now flavor of the year is Telegram, right? Okay. By the way, can you actually download the structure from a Telegram, or like connections, people and connections? Not sure. Yeah, but you kind of follow other people, right? So you follow groups. You have follow channels, right? Oh, you cannot see it. Okay. Okay, so you can say person and the channels. Right. Okay. So in this sense, Twitter was more interesting because you can actually see this sort of flow. You can see how somebody said something and how it actually spreads through the media, right? And I mean, Twitter almost died. but it's U.S. president who pretty much saved the Twitter by choosing to talk to the world through Twitter, which is just no comments. Yeah. Though on the other hand, maybe it's better to do it that way than through the press secretary, which, okay, no comments there. Here is another interesting story. How many of you heard about Enron? What's Enron story?
I heard it was like a company which was supposed to be the next big thing, but then just collapsed or something, like stock crash or something like that.
That's a very sweet way to talk about them. So those were like pretty much biggest cheaters in U.S. history. They're energy traders who actually created fake accounts, trade fake energy, and pretty much it was a huge bubble. Eventually they collapsed, taking down with them one of the companies who were auditing them because they were faking reports. So that was a huge scandal. But the point is, because this whole thing went through U.S. court, in U.S., all the evidence that goes through the court proceedings, they become public. And so all the internal emails, the communication between all the top brass within the company, they became public in the court proceedings. And social scientists were extremely happy about it. Of course, they grabbed the data and start plotting emails, how people talk, and how they send messages, because that's very, very rare occasion when you can get like actual email data, right? So you have who send where, the content. And in the center, the CEO and CFO, et cetera, et cetera, et cetera. So you can actually analyze that. If you want to look closer, there is also a source for this data. Of course, financial data. If you look at this, you might recognize bench of banks, and in fact, this data is about banks loaning money to another bank. Sberbank is not here because it's not like Russian example, right? But the point is, if you look at this and think about it for a second, you realize that collapse of one single bank can cause a very strong chain reaction, right? This is like sort of global financial system. Again, Russia. I don't think there's any of Russian banks in here, but again, amazing that this data is actually available, right? So you actually know which banks borrow from where. So one of the topics we're going to talk about is actually stability of the network to attacks, right? An attack meaning removing certain nodes or certain edges. So what happens if you cut out one country, right? What happens to the entire network? If it's going to collapse or it's going to like disintegrate? What happens if you remove one bank, et cetera, et cetera? Of course, transportation networks, yet another example. Again, it's terrible resolution on this projector. I wanted to ask if you recognize the CD, but yeah, now it's kind of useless. Oh, and it actually says it. All right, forget it. And another example from biology, this is protein interaction network. So every node is a protein, and if they're connected, they're interacting. Now, again, notice the reason and the point of me showing you all these pictures is to show you that, well, there is some similarity in between all those graphs, right? They're all kind of, complicated, messy structures. In all of them, you see this, again, like tree and branch-like things, right? And you see some nodes with a lot of connections, others with fewer connections, and then there might be groups of nodes that are tightly connected, et cetera, et cetera, et cetera. So that's sort of what made scientists think of existence of some universal properties that you can use to understand the networks, and maybe existence of some universal laws that actually guide the creation of those networks, right? So that's sort of what the underlying thought. And those of you who are interested in this, there's actually a terrific website, which is called, again, I don't know why. Actually, I think I know why it's not showing. There you go. Smart. There is a terrific website which is called Visual Complexity that has tons and tons of very cool visualizations. And the best part, they're actually not just collecting pictures, they're also pointing to the authors and to the author websites. And so you can, in many cases, you can go and download and get the data itself. And sometimes you can get even like code that authors use to create this, right? And they're like, there was amazing things in there. Okay, so as I mentioned, there is a sort of the complex network, the complexity of the networks. We need to come up with some metrics that characterize them. And there is a sort of three fundamental things that scientists noticed back, again, 20 years ago, and start talking a lot about it. And they became sort of the main three properties of these networks. Now, you need to take this a little bit with a grain of salt right now because, I'll show probably in the next lecture or next time there is this like very interesting discussion happens right now between scientists about the universality of these properties. And there are sort of people who believe that the properties are universal, and the fact that we don't see them right now in all the networks just means the network data is dirty, is noisy, and so but the properties, those fundamental properties exist. So other people saying like, okay, this is BS, right? They're not fundamental. It just happened that you notice them, but in fact, life is different, right? So it's actually interesting to observe this discussion right now. But so far, I'm actually more inclined to think that those fundamental properties do exist as sort of like sort of gravitational law, other things, but in the way they express in everyday life. Again, data is noisy and things are not perfect. And again, if I try to, take this paper, sheet of paper and drop it and calculate the gravitational force, right? I would say, well, Newton is wrong. So, so you need to be very careful with those things. But, the ideas are beautiful, so let's talk about this. But they are sort of a little bit of the spherical cow uniform distribution of milk, which is, about ideal system, right? Okay. So first of all, the fact that these networks are so-called scale-free and have a very particular degree, no degree distribution. We're going to talk about it in a second, but the idea is that in these networks, all of them, there is a very particular degree distribution. Degree distribution is a number of nodes of certain degree, right? So number of nodes with certain number of connections. So, in plain Russian or English, it means if you think about social network, there are people who are celebrities and they have millions of followers and friends. And they're like rest of us who has, how many friends do you have on Facebook? Oh, God. Okay. How many friends do you have on Facebook? Don't tell me you don't have Facebook. 100. Okay. What's your number? 30. Okay. You don't have Facebook contact? Oh, my God. How many friends? 400. All right. Any large number? 600. All right, cool. Anyway, so there is like 400, 600. Okay, fine, 20 friends. But that's what like normal people do have, right? But then you have like celebrity, and then it's, 10,000 friends or 10 million friends. And what's happening is there are some nodes that are very large in terms of the number of connections, right? But the majority I actually have very few connections. And so there is a huge sort of unevenity in this, right? It's very uneven, distribution very uneven, right? And that's we're going to talk about this. And it's actually called power law, but I'm sure you heard about Pareto distributions, right? Or zip, right? Do you know what zip distribution? If you know, can you tell us? Can you remind us? Распределение цыпфа или зипфа. Distribution of the frequency of the words that in language. Do you know this? Oh. So the frequency of the words is distributed, the usage of the words, right, is inversely, so you can rank the words by the inverse, okay. If you rank all the words by the frequency of its usage, of their usage in language, right? You can rank all the words by the frequency of the usage in language. Then the frequency will be proportional to inverse of the rank. So the second word used twice, like half times as the first word. The third word is used 1/3 times as the first word. The fourth word used like 1/4 of the times as the first word. It's very powerful law. I mean, of course, in the real language, it's not precisely observed, but that's sort of one of those power laws thing. I'm going to talk about it right now. Then the second property is a small network, or small world network, which is a small diameter, or as we discussed already, it's really sort of small average path length. I'm sure you heard about this 6 degrees of separation. Heard about it? What is it?
It's like you can reach any person through 6
handshakes. Yeah, so 6 рукопожатий, right? So 6 degrees of separation, that every world is connected through like 6 people. That's sort of the fact that it's small world. And the point is that these networks are very, very compact, right? So there are always a very short path from one end to another. And we're going to talk about that property. And the third property is what's called high clustering coefficient or transitivity, the fact that in many of those networks, there are lots and lots of triangles. And if you think about social networks, it's kind of sort of a little bit obvious, because in a social network, it is, what does triangle mean? It means you have 2 friends, right? So if they know each other, that's triangle. So the way we actually meet people, the way we interact, it actually forces us to create those triangles, right? So social networks, there are a lot of those triangles. But surprisingly, in many other networks, there are also lots of triangles. And that's called, high clustering coefficient, because clustering coefficient measures how many triangles are in the network. Or also, people talk about transitivity, which is the same. Transitivity means, you probably remember from math, is if A equal to B, B is equal to C, then A should be equal to C, right? So if A is connected to B, A is connected to C, so B then is connected to C. That's where that's the notion. That's where the word is coming from. But the point is, there are these 3 fundamental properties, and if there is anything you need to remember out of this sort of network science course, or like complex networks, then there is these 3 magical properties that more or less hold across all of these networks, which is this very strange power law degree distribution. We're going to talk about it in a second. There is the fact that there is a small world networks, small diameter networks, and the fact that there was a lot of triangles or high clustering. Now, there are many more properties, but these kind of stand out. Okay? All right. So, power law distribution. What is this? Now, we don't have much time, but let's make this quick experiment. What's your height? Yeah.
1.8.
Okay. Yours, gentlemen. Yeah. 180. Yours. 195. Good. What is... Come on, don't be shy. I'm not asking your weight. All right, what about you? What about you? 170. What about you? Okay, what about you? Okay, so if you, we didn't write it down, but you kind of also like hearing it. It's like around 180, right? So on average, probably a lot of people like 179, 180, right? And then there is this distribution, which is typical sort of Gaussian kind of shape distribution, where some people will be like, 170, will be somebody 165, and there will be somebody 195, and there will be somebody 2 meters, right? So that's sort of the typical, distribution. Now, what you don't see is somebody who is adult and 50 centimeters tall. Most likely, okay? And you most likely will not see somebody who is human and 10 meters tall, right? So that just, it just doesn't happen. So if you think about the distribution of the height of, human person, for males, you have probably, I don't even know where it's centered here, but somewhere around maybe, 180, right? And then there is a sort of bell shape. And then the tails are very, very, they're very weak in the sense they're like goes down very fast, right? It's like sort of very fast decay. And, you never meet in the nature somebody who is far away, to the left, right? Very short and very, 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 very tall. And so that's the distribution people use to deal with. Now, surprisingly enough, there are other distributions that exist in the world. And there are quite a lot of them. And there's a distribution we are particularly interested in is called power law distribution, where the distribution, that's terrible projector, where distribution looks like this. It drops down and then, stays flat, right, for a long time. So it's very fast decay. Now, when you have picture like that, like what you see on the left, it's a good idea to actually plot it in the log scale. So you do logarithm on horizontal axis and logarithm on the vertical axis. And then, for a very particular type of distribution, which is called power law distribution, you're going to see there a straight line. Now, so what's power law? Power law, it is, what's in its name. It's a function, it's a distribution that is f of k is c, where c is a constant, divided by k to some power. Gamma is a power. Or you can write it c times k minus gamma. So 1 over k squared is a power law. 1 over k cubed is a power law. 1 over k to the 10th is a power law. 1 divided by k in the 2.5 is a power law, right? So 1 over x is hyperbola, right? So we saw it in high school. Then there is 1 over x squared, 1 over x cubed. They're all power law distributions. Now, if you think about those functions and you take logarithm, you realize that if you plot log of the function on the y-axis as a function of log of, in this case, k, right? So log on this axis, log on that axis is going to be a straight line. Make sense? Oh, come on. Yes, right? 1 divided by x squared, if you take logarithm with what's it going to be? Log 1 minus log of x squared, right? Log of x squared is going to be 2 log x. So if you plot it as function of log x, it's going to be a straight line with a negative slope of 2, right? Okay, so the picture that's shown here is actually the number of cities, and on the x-axis is a population of the city. And so what happens is there are several cities in the world that has lots and lots of population, and the majority of the city is actually very, very small. And so compared to the human height, the size of the cities, right, distributed not according to Gauss distribution, but according to power law, which means there are several cities that are huge, and there are lots of cities that are very small. And this type of this type of networks, this type of distribution exists in a lot of cases. For example, like as I mentioned, the first one is a word frequency, which is how much different words are being used. Then there is citation networks, right? So there are papers who are cited by everybody, but the majority of papers are actually like very lonely, right? They get like one citation by the same author later on in life, right? But so there is this huge skew in this distribution, and if you plot that, like the number of papers with the number of citations, you realize that it also follows almost straight line if you're in a log scale. And books sold. There are some books that are very popular, right? There are few titles that are extremely popular. Everybody buys and reads them, but in fact, majority of the titles are not very popular, and people just don't buy them, don't read them. In fact, that's the business model of like Amazon, right? The reason is they're actually selling books that you typically cannot buy in a regular bookstore. Because everybody can, bestsellers is trivial, right? You order 10,000 of those, and in the bookstore, and they're going to be gone. Very easy business model. It's extremely hard to service people who want a very rare book. Because when I come to the store, I want this book, right? The store doesn't have it, so they have to order. I have to wait a month, so that just doesn't work. And Amazon benefits from it because they either have like centralized location where they do have rare books, and so people can buy it, or they can actually, print to order. And in fact, because if you look at the distribution, again, most of the books, majority of the books are kind of in a rare book situation where they have only a few purchases a year, but there are a lot of this type of books. And so as an aggregate, it actually creates a lot of money. And so you cannot do this type of model with a brick and mortar store because you just cannot store all those books. And so that's what made Amazon is by selling products, not that they're blockbusters, but by selling this long tail of products that are not that popular. Make sense? Sort of, kind of. But the point is, if you again look at this books sold, there is this bestseller books. There are a few of them, but they're sold in 1 million copies. But the majority of books are sold actually with a fewer copies. So we're going to work for another hour, then we'll be done. So this is a picture we paused on this power law distribution, this notion of that you have a very, very uneven distribution. And we're going to talk more about sort of what it looks for networks. And I hope you at least can see this type of diagram, and I'm going to focus on it for a few seconds. Now, think about what you have on the right-hand side is this. Can actually somebody explain to me what's on the right-hand side? What's this diagram? Flights, right? So the way world airlines organized is through this what's called hub and spoke system, where you have big hubs that is connected directly, right? And then you have to change planes and go to a lot of little cities. There is no reason to connect Moscow with, well, yeah, there is no reason to connect, I don't know, London to some, small tiny city in Midwest of United States, right? But you connect London to Chicago or Boston or LA, and from there you fly to the small city. So that's the way world travel is organized. And the reason I'm showing that graph is because those cities with lots of connections are called hubs. And I mean, they're called, airline hubs and, the network, they're hubs. There are a few of those. You can probably name me, like what is the top, airline hubs in the world? Moscow, well, sort of, kind of, probably number 10. But locally, yes, but in the world, globally. London, Heathrow, yeah, and then there is Paris, right? New York, Dubai, Amsterdam, right? So probably a couple more, but that's about it, right? So we can count them easily. But how many airports are out there overall? More than, yeah, I mean, I don't know, actually, it's a good question. Google, I'm sure, knows, but probably close to 1,000 if you take like small regional airports, maybe even more, right? We don't know about them. But the point is there's huge hubs. There are a few of those, right? But they're like really big. From there, you fly a lot of places. And then there are like lots of regional airports, small airports, very few flights comes in and out. So if you think about and try and look at that as a diagram, as a network right now, right? Then what you should understand is there is this type of distribution we can show. On the x-axis, we'll show number of links or number of neighbors or number of cities this airport is connected to. There has direct flights. And here, how many of those airports are out there? And right here, what you see, it's inconveniently even showed as a cartoonish. Here, it's the airports with, say, one connection, right? Only one direct flight to that airport, like little regional airport, versus like LA, New York type of airports with lots of flights. And so the point is, this is number of links. So it's on the right because it has a lot of connections, right? So it's a huge airport. But how many of them? Just very few, right? This is how many of them, that's how many links they have. This is like very small regional airports, but that's how many of them exist in the world and exist in the network. If you think Facebook, this is people, these are celebrities, people with lots and lots of friends, but there's not that many of them, of these people. Normal people live somewhere in here with, a couple hundred friends. I mean, couple hundred friends, couple hundred links, and that, probably millions of those people. And then there are other people with very few friends. Okay? Now, according to this story, actually the world is a very lonely place. Majority of people have like 1, 2 friends. Surprisingly, if you look at social networks, that's actually pretty close to be true, right? Not exactly. So, closer to this part, we kind of move away a little bit from this power law distribution, but it still has this tendency. Now, if I take this graph, and instead of number of links, plot here a logarithm of number of links, and instead of number of this type of nodes, I plot logarithm, what am I going to see here? Straight line. Okay? Now, this is in the perfect world, right? In the real world, of course, it's not going to be perfectly straight. But does this make sense? I mean, guys, this is like the key slide in the whole discussion. Does it make sense? All right, good. So, again, number of links, which is number of friends, number of connections. Sorry. Number of friends, number of connections. This is how many of those connections are. Now, this is actually a very cool graph, and I recommend you later on go and look at it. This is a history of philosophy. And so, again, the resolution is terrible. Oh, by the way, something else. I have all those slides there on the website. And so, if you have your computers, you can actually also see them. Go to the website, and you'll see the slides in normal resolution. Anyway, these are different philosophers through all ages. They're connected to their students or followers, right? And so what it shows you that there are thousands of philosophers in the world. And all of them write something. But there are only a few of those that are big that have a lot of followers. You can probably guess the names. Come on, let's test it. Can you actually read it there, or you know? Oh. Right. So I could zoom in, and yes. So the largest sort of number of followers. Yes, Plato, and there is Marx somewhere in there. But the point is, the structure is surprisingly, I don't want to compare philosophers to the airports, right? But the point is, yeah, there are a few of those that are very large, very well connected, but the majority are much, much smaller. And if you try to do this distribution, it will also look like the distribution for the airports. And that's the sort of universality of the property, right? So you can look at the different networks from the different types coming, nodes means very different things, and they formed very differently. But somehow they get very similar statistical properties, right? And that's what was puzzling, and that's sort of what started this as a science, where there's something universal happening here. And we'll see this over and over and over again. Okay, that's power law. All right? Make sense? Makes sense. And by the way, for the first time, it was kind of discovered, or I wouldn't say discovered, observed in the world, in the sort of real wild world, in 1999, by the guys working on the search engine, because they did a World Wide Web crawl, and they looked. It was IBM, and they looked at the frequency of. They looked at every page and how many pages points to it, right? And how many pages the pages points to. And they found out that, yes, there are some sort of hubs, pages that have a lot of followers, following a lot of pages that points to it, right? But majority of pages have 1 or 2 incoming links, right? And if you think about it, CNN or White House, that sort of web pages will have a lot of followers, or maybe some celebrity. Anyway, so that's sort of the prehistory for that story. And we're going to talk a little bit more about it. Now, the second story here is, this comes actually from sociologists. And this is very, very famous paper by Mark Granovetter. It's called The Strength of Weak Ties. And he looked at, connections in social networks. So that was actually the studies, before the network science, as a science happened, before, you had all the computers. But he's a sociologist, so he studied relationships. right? And he actually looked at these triangles, and he called this a forbidden. What you see here on the right is this forbidden triad, which means he's saying like if A is connected to B and A is connected to C, well, there should be a connection between A and C if it is a social network, right? So he's pretty much saying that there must be triangles. And that's sort of, this must be thing, of course, came from, his studies of sociology and this whole notion of like how you meet people and, two people, if you have two friends, they most likely know each other. And A and B and C are strongly linked, which means there is this not just sort of your abstract Facebook friend, like one of the 600 friends you have, but this is the connections that you maintain, which means, you talk to people, you interact, you write, you meet, right? So then there is this forceful, there should be a connection between B and C. 1973, that's when the paper was published, right? And that sort of kind of traces back this story of triangles in the network. And, there is like a lot of studies, recent studies, of course, when you have like Facebook, you have the network, right? You can actually just calculate those things. And this is an example, again, unfortunately, you can barely see it, but this is, from the study from the actual Facebook guys on a friendship. And again, when you see this in a good high resolution, you will see that there are lots of triangles in there, which is quite obvious. You can just look at just out of curiosity tonight, just look at your friends and see how many know each other. And you'll be surprised, especially if some of them, you would never think that they know each other, but they do. So, and of course, the other story is about, triangles and, say, citations and co-author network, right? If you think about somebody, you write a paper with somebody, right? But he wrote a paper with somebody else, then the next paper you might write together with them, et cetera, et cetera. So it's kind of spreads. And again, there are like lots and lots of triangles in there. So it's quite natural having triangles in social sciences. It's much more surprising that there are triangles, in web graphs. It's the triangles in other type of networks, but they do exist. The other story is like the famous story is, with the small world story of 6 degrees of separation, and Stanley Milgram, 1967. Again, it's 50 years ago, right? Now that's an amazing experiment. This dude is famous for 2 experiments. Do you know the other one? It's actually, guys, interesting. I'm teaching this, this course is sort of in-depth network science, computer science, math story. I'm teaching Mago-Lego version of this course, usually in like last semester, which is, light version of this, right? With less math, more discussion. And it has like a lot of people from the university, different people from the university, different students. And when I ask this question, there's always somebody knows the answer because, of the backgrounds. And so it's kind of interesting because network science is very interdisciplinary, right? And when you come from different backgrounds, like different pieces. So for you, like shortest path is obvious, what it is, right? For those guys, it's like Stanford prison experiment. Yes, no brainer. We all know about it. Do you know what that is? Yeah, now you know. It's the same guy who actually set it up. But they don't know shortest path. So anyway, so this experiment is the following. Somehow he got interested in this sort of saying that 6 handshakes separates the world, right? And again, think back 1967, professor, university, how would you test this theory? Let's say, the theory is, the hypothesis is that everybody, in the world is connected through a few handshakes. How would you test it? 1967. Yeah, I'll ask who.
Maybe using scientific papers as research.
There's no emails.
No emails. 1967, dude. There is no internet. All right. He actually did something amazing. He said, okay, fine. You know what I'm going to do? I'm going to find volunteers and make them write letters and try to trace how those letters, like physical letters, how they go through the world. Let me explain the setup of his approach. So he actually published in the newspaper, the ad asking for volunteers, and the idea was the following: I'm going to select a few people in the country, and I'll give you the names and their profession. And the goal is for you to try to take this letter and send it, deliver it to this guy. But the only way you can do it is through giving it or sending it to a person you personally know. So to your friend, to your acquaintance, he might be living in a different place, in a different town, but you should know him. Okay? So you should have this maintained friendship relationship with this guy. And so the idea is to think and, try to, and the only way the last person can deliver it to the addressee is if you know this addressee, like by your first name, right? So if he's friend. It's an amazing experiment, like even just try to do it, but he done it. And this is, in fact, this is a fact, the letter he sent out in terms of how to take part in this study, the instructions. Like today, you can easily do it through email, right? But then nobody will participate because you'll say it's spam, right? I mean, come on. You're asking me to send letters right across. So anyway, so he published in the paper in an ad, and people responded. And so he wanted to do actually a couple things. He found a target in Boston, and so he set up two experiments. One experiment gave out this letter to volunteers in Boston and asked them to send it, to deliver it to the guy. And then he went into the middle of the country to Nebraska and published there. And so the starting point for letters was Nebraska. And so he actually got like almost 300 volunteers. Oh, and by the way, when the letters is being transferred from one person to another, you have a ledger, and within the letter there's a ledger. So I send this letter to this guy, okay, and then he writes, continues the ledger. So when eventually the person in Boston receives the letter, if he receives the letter, there is a ledger through how many steps it went through, okay, and so there was a target person, Boston stockbroker, 196 people in Nebraska, 100 in Boston. Information given, target name, address, occupation, place of employment, college, hometown, blah, blah, blah. But again, you're only allowed to give it to a person who you know personally. And the most amazing part, that 30% of the letters actually reached the target. So 1/3 of the letters were delivered. And the average chain length was 5.2. And so that there was a confirmation of degrees of separation. What you see on the right is number of intermediaries, right? So the length of the path, the way you talk it right now. And on the vertical axis is the number of chains or the number of letters that went through that. So you can see that 15 letters went through 6 intermediaries, etc. Right? What's surprising about, of course, it's statistically a very small sample, but still kind of curious. And there is also, if you notice, this graph has 2 peaks. Right? What do you think? Why do you think it is? Is it just noise or? It could be noise, right? Because there's just very few data points, but still, yeah. 2 different strategies. One strategy was the sort of hometown strategy. So, if you were asked, if you have this kind of task, let's say I want you to send a letter, to deliver a letter to somebody who lives in Novosibirsk. What do you do? But do you know anybody in Novosibirsk? Okay, crap. Okay, I want a letter in Abu Dhabi. The chances you know somebody there is probably 0, right? Okay, what do you do? Who do you send a letter to?
I send a letter. No.
Right. So there are a couple options. One option is you can go through your friends and think who is, like you said, from Novosibirsk. So it's the location story, right? Or maybe you're going to say, okay, well, Novosibirsk is there, it's Siberia. Okay, let's say maybe I can send it to Chelyabinsk, right? I mean, just should go that way, right? Or that's one option. And the other option, what they also knew is a profession, right? And so they said, oh, he's a stockbroker. Let me send it to the stockbroker I know. Maybe he knows other stockbroker who knows, And so those two chains actually correspond, two peaks corresponds to different strategies. One strategy was through business. One strategy was through like sort of place of birth, right? Location. And in fact, hometown strategy was longer than business. So in some sense, business world is smaller than the hometown world in some sense, right? So the network of business connections is tighter, according to his experiment. Right. Yeah. So that's what I'm saying. Like business network, professional network. So I give to somebody who is of the same profession, and then he within his professional network, looks for people in another town because you think the professionals are connected in different towns. But anyway, look, this was the experiments. If you're interested, I mean, it's pretty cool. 1969 published, so it's online, it's available, read it. It's actually quite entertaining reading. And also, of course, if you start in Boston, it's shorter than if you start from Nebraska, which is kind of obvious. But, again, the amazing part that he got it like 6, right? 5, 6, which was like insanely surprising. And so it was the first confirmation of the 6 degrees of separation tale, right? Of course, when computer scientists joined this race in 2000s, of course, there's like a lot of ways to do it, right? 2001, back then people still used email like easily, right, without being concerned too much about spam. So there was a study done by Duncan Watts. Then there is a study which actually emails and sending out emails. Then there is a Microsoft Messenger. It used to be Microsoft. I don't even know. Do they have Messenger now? Well. Oh yeah, they bought Skype, right? Now it's Microsoft Messenger. So yeah, so they had Messenger, and there was a Messenger graph, 240 million people. So you actually, the guys, Juri Leskovec, he actually had this graph, like he worked for Microsoft back then and as an intern, I think. And so he actually can calculate this average path length, right? 6.6. Now Facebook did it when they had like 700 million users, and Facebook actually much tighter. It's 4.7 back then, right? And they also notice interesting properties. If you look at those pictures, you realize one of them, different colors here are different, so the different timeline, right? And so darker is 2011 and yellowish is 2009. So the point here is that network getting denser. So in a sense, like the shrinking with time. I mean, kind of natural, right? You get more people, you get more connections. But of course, those things has been calculated, and still, it sort of amazes you, right? There is this like billion people, right? And it takes only 5, 6 handshakes to get from any person to any person. Like it sounds insane, right? Is it possible or not? No, I mean, okay, but like, maybe we're making like some huge mistake. Maybe we just don't understand something. Like, if you think about this, if, for example, for a second, let's say we have 100 people, right? And the network is structured the following way. It's sort of, let's say, think about dachas, and you know only your neighbors. Right? That's your dacha. That's like, I don't know, what, 4 people you know. And next knows 4 neighbors, and next knows 4 neighbors, and next knows 4 neighbors. And that's it, right? So the world's friendship is organized on the grid. Okay? So every node has 4 connections, so knows 4 people, another person knows 4 people, another person knows 4 people. Right? If we have this type of grid, and let's say we have 100 people in it, what would be on average the average path lengths? Well, the diameter, first of all, here. 10 by 10 grid, 100 people. What's the diameter? 10. No, because if it's 10 by 10, like reaching the furthest, it takes you 10 steps. On average, maybe it's going to be like 5, 6. But now think about, okay, you have 10,000 people. Or, I don't know, million people, right? It's a grid of 1,000 by 1,000. So you think it takes 1,000 handshakes to reach the person. We're saying it takes, what, 6 handshakes for 6 billion people. It's clear that the world is not organized in the sort of cell fashion where, you have 4 friends and the next friend has 4 friends, et cetera, et cetera. There are there is another structure. And surprisingly, and that's Facebook picture, surprisingly, you can think of very, very simple structure that actually hold this type of properties easily. Can you actually see edges there? Or barely? Barely, okay. So the point is there is a node in the center, and the node has 1, 2, 3, 4 friends here. And then each of those friends, actually, let me see here. Yeah, and each of those friends has 4 extra friends, right? And each of those friends has 4 extra friends, etc., etc. But the trick here is these are new friends, right? They're not overlapping. If you think about this, let's say you have 10 friends. Okay, you're not that lonely. All right, fine. You have 10 friends. Each of your friends also has 10 friends. What's the circle of friends overall? Approximately. 10 times 10, right? I mean, well, that's fine. We've done double count. It's 9, but who cares? 10 times 10, 100. Each of them has 10 friends. So if you go for the third level, it's going to be 1,000, right? Okay, good. Now, let's say you have 100 friends, which is on average you have, right? Now, it's 10 to the second. Each of your friends has 100 friends because they're like you. It's 10 to the fourth. Each of your friends have 100 friends. It's 10 to the sixth, right? And that's already, by the way, it's 1,000,000, right? Then one more step, it's 10 to the 8th. One more steps, it's 10 to the 10th. It's 10 billion. So pretty much, if you have 100 friends, in 5 or 6 steps, if those friends do not overlap, you reach 1 billion. You reach 10 billions. So it's amazing how fast this grows. So the point is that if the world was organized like this, and there is a contradiction here. The contradiction is what it says is your friends don't know each other, right? And we said that, okay, there's this triangulation in the social world. But if there was no triangulation in the social world, then it's very easy, right? Just having 100 friends, on average, makes 6 billion in 5, 6 steps, which is kind of surprising. I mean, you don't expect that it grows so fast, but it does. So it is possible. I mean, first of all, we observe it, and it is actually mathematically feasible. Of course, the real graph is different. Of course, you have triangles, et cetera, but this kind of makes much more sense than when you look at the grid, right? And then to reach 10,000 people, you need 100 steps. So that tells you something about the structure of the network. So the real-world network is structured not on the grid, but structured more of this kind of very fast growth in terms of number of friends, right? And that is sort of the secret to this small world feature, right? The particular way things are connected allows you to traverse from one end of the graph to another end of the graph in a very few steps. Also think about for a second about airline network. What you really need to do is to get to a big hub, right? Then you travel internationally long distance, and then you travel another leg for one more travel and you connect to very, very far away, small, tiny, teeny cities, right? In 3 steps, maybe in 4. But if all the network organized that way, then it is possible that the world is actually small, right? Okay, so that was a small world story. One last thing, and we have very little time. There is actually the good news. Back again in 2000, it was you had to collect the data yourself. Right now, there are actually very, very good repositories of the data. And when we start talking about homeworks and then later on projects, I strongly recommend you to go and look up the data. The Colorado Index of Complex Networks, supported by Aaron Closet, he has like probably 4,000 or 5,000 networks, and you can select what type of networks you need and download it. Stanford Collection, UCI network data repository. So there are plenty of networks available for experimentation. And some references here. These are kind of classical papers, 2003, scale-free networks, some reviews, and then there's like a little bit more of papers on, 4 degrees of separation, and that's a Milgram paper, 1969, and Small World paper, 1967. So the papers, the references are available on the site, and probably the papers also. That's it with the sort of introductory part. Any questions? Concerns, complaints? Yes? Yes, and that's actually a very good. That's a very good comment. Obviously the experiment, when they did the sort of Facebook graph, that is, pure mathematical shortest path, right? It's being computed, right? I mean, yeah, that's computed. That's no questions. Now, but with Milgram experiment, yes, that's a very good argument that, there is no proof that this is the shortest path, right? I mean, there is no proof, but. And I mean, you cannot argue this criticism. It is the path that has been found. There is a much more interesting question: is how in the world did we find how could he find that path? Like, what was the logic when you have this type of network? How human can actually find the right shortest path without seeing the network? Like, computers are dumb. If we want to find the shortest path in the network, what we do, we'll go through freaking all the paths, right? Which is insane. Which is like n squared, n cubed, like n squared pairs plus whatever it takes to calculate the shortest path. It's I think it's n cubed algorithm, right? Also, all shortest path. You don't do this, so it means people do something much smarter than computers, which means we need to understand what they do and then teach computers. And there are a bunch of papers trying to actually explain the logic. And I don't remember exactly, but I think there's something about like adding geo coordinates that kind of helps us. But there is no good answer. The same story with teaching computer play chess, right? There are every time on every step you make in chess, right? There are so many options. How do you actually trim the tree? Of your selections. How do you choose the right way to play the game? Now, but you're absolutely right. I mean, in the original experiment, no, there was like a lot of criticism to this experiment, and like, to tell the truth, if the result were not 5 or 6, this experiment would have been forgotten, right? But because the result came out as 5 or 6, it was amazing in terms of how short it is, and it's also amazing in terms of like that it actually matches the sort of the story of 6 degrees of separation, which existed before that.
We also can say that average path between people is top estimation of profit.
Yeah, exactly. So it is the top estimation. Oh, that's actually a very good argument, right? So it's estimation from the top of the shortest path, right? We cannot guarantee that this is the shortest path, but the shortest path should be smaller than that, right? And so that's a very good point. So, yeah. Anyway, but again, because it was so small, that's why it is kind of remembered eventually. All right, so let's switch to the next lecture. We'll probably cover half of this material, and then some other stuff will be covered during the seminars and next time in the lecture. So, power law distribution, as I said, this is very simple. You have a node degree. Node degree is the number of nodes that that are neighbors, right? Number of nearest neighbors. If we can say n sub k is number of nodes with degree k, total number of nodes is the sum over n sub k. And so degree distribution is really a fraction of the nodes with a particular degree, right? Here you have 4 nodes. There is 1 node of degree 1, 3 nodes of degree 2, and that's, 1 node of degree 3 and 2 nodes of degree 2, right? That's your histogram on the right-hand side. And that's your sort of distribution of node degrees. On the bottom, you have a circle. Every node has degree 2. That's what you see. By the way, sometimes you will see in the lecture and in the course in the science a lot of sort of very artificial creations like graphs you will never see in the real world, which is like circle. That comes from physicists who love to find like very nice, very simple models. Some of you maybe remember, or if you did for example, differential equations, the favorite story is like periodic boundary conditions. So you can connect the start with the end so you don't have to deal with boundaries. Anyway, so there's like very simple models that you can actually easily understand and analyze. Anyway, just 1 degree, right? One type of. Now, this is another graph, which is, it's actually a famous graph. It's called karate graph. The story is there was a karate studio, and it became famous after somebody in network science grabbed this graph and start using it to check different algorithms. There is really nothing particularly special about this graph except for the following. It is really friendship in a karate studio, and that is a study done by sociologists, and it's a longitudinal study, which is they looked at this karate studio, as things evolve in time, and they had internal conflict. 2 instructors, and the studio split. And some students went with 1 instructor, another with another instructor. And so that gives you sort of ground truth in terms of how many clusters or tightly connected groups were in the friendship world, right? And that graph became famous, and now it's being studied all over, always. It's called Zachary Karate Club. You'll see this reference millions of times within the network science. But the point is the distribution, right? So what you see is, again, there are a bunch of nodes with degree, 3, 4, 5, and there are a few nodes with degree, like 2 nodes with degree 15 and 16, right? So it's very uneven distribution. Now, if I take on a little bit more complicated graph, and again, I apologize, you cannot see all the edges, but this is, degree distribution in some network. You will see like very strong core, and then there is sort of tree kind of things. Spike goes around. You can also calculate for this graph degree distribution, and it will look already more like what we see before when we talked about power laws. Again, the story is majority of the nodes. Oh, and by the way, vertical axis can be calculated either as you actually count how many nodes with a particular degree you have, or you divide it by the total number of nodes. And then it's going to be a probability, right? If you pick up a node, what's the probability that this node has a certain degree, right? So degree distribution, if it is normalized, then it shows you the probability. And so what it means, if you randomly pick up a node here, there's a high probability to have a node with a low degree, right? And low probability to have a node with a high degree. Okay? Make sense? Again, in plain language, just few nodes with high degree, lots of nodes with low degree. And if you take, take yet another graph, you don't see it here, but I can take that graph and calculate again distribution, right? So not degrees, how many nodes? It looks like that. Sort of elbow curve, very, very sharp drop, and then you don't see anything. And it's not because there is a bad projector, it's just because the graph is like that in the scale, because the scales are so different. And what you see on the right is the same picture shown in logarithmic scale, right? And that already is sort of, and that's like real world data. And it's not a straight line, but it is very close to a straight line, right? So on the next slide, I'm gonna zoom into this. And what you see again, on this vertical axis is the logarithm of the number of nodes. And on the horizontal axis, are those node degrees. Now, how to understand this graph? Well, very simple. So what you have here, right? This is a node degree. And this, the corresponding y-axis is how many nodes of that type you have. So it says you have one node of this degree, one node of that degree, one node of this degree, and this is the highest degree node. But just the only single node like that. So these are all nodes that unique in terms of their degree. Now, with this degree, there are two nodes of this degree. Right? Then there are 3 nodes of these degrees, 4 nodes of these degrees, etc., etc., etc. And the majority number of nodes have this degree. So this is how many of nodes? That's their degree. Make sense? I mean, if you're not used to seeing this type of graphs, well, it will take a little bit of time to get used to it, but after that, it's going to be easy to understand. Now, the thing is, though, if you look at this graph, you realize, yeah, you can try to map a straight line to this. Remember, this power law is a straight line on the log-log scale. And, there is clearly a part of it where you can map a straight line, but not everywhere, right? And so the question is, if this, if we need to use some different technique, or if it is, the data itself is not this power law thing, right? And we're going to talk about it in a sec. Now, this is a comparison that we actually, this is pretty much the slide I shown you before, where we're comparing, power law, which is the bottom, and that's what we saw, to like more of, traditional degree distribution. And the traditional degree distribution here is sort of simulated or shown with a road network in the United States. So showing that cities on average, because it's like geometrical, if you think about the roads, and the node degree will be the number of roads or freeways that live in the city. I mean, in the US, it was strategically designed in a certain way to actually have like horizontal and vertical freeways. And that's why, the distribution is very bell-like versus the distribution we saw previously, right? For airlines, it's a power law distribution. So, a little bit of mathematics. We're going to go quick through this. We can spend more time at the lab. So when you have a power law distribution, it's a probability of a node having certain degree is inversely proportional to that degree. And there is a coefficient proportionality is gamma. And that gamma is different for different network. It can be, 2, 3, 2.5, 3.7. Different networks have different coefficient. But the point is that the probability of having particular node degree is sort of inversely proportional to that degree into certain power, right? And so you instantly understand that if node degree is low, like k is equal to 1, the probability is high. If k is equal to 1,000, the probability is low, right? And that's what you see on those curves. Now, if you take log-log, of course, you get a straight line. Since, in this case, if it is a power law distribution, if it's a discrete distribution, then k is a discrete number. It's a node degree. It's 1, 2, 3, 4, 5, whatever. It's a number of neighbors, right? It's an integer. So in order to normalize, for example, to actually calculate this constant c, this coefficient, you need to just sum up everything. And it's called Riemann zeta function, and you can calculate it. Or if you have a real graph, you just add up the numbers, right? Because here it goes to infinity. If you have like infinite graph, if you have like, real experimental graph, you just add up node degrees. Now, physicists being physicists, they said, okay, look, it's pain to investigate sums and work with integers. What's much easier is to relax and assume, just for sort of purposes of computations, that node degree can be just a real value, okay? And then you replace summation with integration. Some of you who took some of the probably math classes, well, you know those tricks that being used when you can look at the integral, at the sum, you cannot take what you do. You approximate, instead of sum, you actually take an integral, because you can take that integral, right? And then you estimate the sum by two converging integrals, by showing where it is. So the same idea is here. Let's for a second assume that no degree is not necessarily integer, right? It can take real values. And then instead of, like to do normalization, instead of just doing this crazy summation, we'll just take integrals. And then we can actually see, if it's easily converges, diverges, et cetera, et cetera. And then you start observing very, very interesting things. You start observing that this coefficient gamma is very important. That in order for the integral to actually converge, this gamma has to be greater than 1. Why? Well, if you take gamma equal to 1, you have an integral dk over k. What is it? Okay, what function you need to differentiate to get 1 over k? Logarithm. What happens with logarithm on infinity? What is it equal to? Diverges, right? It's equal to infinity. So the integral diverges. Now, think about this. If your integral is 1 over k squared, you integrate 1 over k squared, what is it equal to? What do you need to differentiate to get 1 over k squared? 1 over k, right? It's minus 1 over k. Derivative is equal to 1k squared. So if you integrate 1 over k, okay. If you take then this 1 over k at the limit k goes to infinity, it is 0. So that's integral converges. So if you want to be able to normalize, your gamma has to be greater than 1, because if it is 1, it's logarithm. If it is greater than 1, then when you integrate it, it still converges on infinite limit.
Gamma is integer number?
No, gamma is not. Gamma can be, it's real number. So it can be, 1.1, 1.2, 1 point, whatever. It's just required to be greater than 0. But in order for this normalization to exist, gamma has to be greater than 1. And that's that's what we're going to observe a lot. But it's actually getting even more interesting. Let's say you calculate different moments of this distribution, right? What's a moment in the distribution? Well, it is, average. It is, variance, right? You calculate k squared, average of k cubed. So that's what moments are. You quickly can realize by looking at these integrals that gamma has to be greater than 1 for normalization to exist. But in order for average to exist, gamma has to be greater than 2. Because, how you calculate average is k times p of k. Well, that is dk divided by k gamma minus 1. And that integral will converge only if gamma is greater than 2. Which is very bizarre, right? It actually says that in your sort of distribution, in your theory, in order for average to exist, gamma has to be greater than 2. In order for k squared to exist, gamma has to be greater than 3. And so on. So, well, it is strange. But on the other hand, in the real world, when you deal with the real networks, you don't sort of have, infinite network size. They're all finite. So, all those values will exist, but why is it sort of concerning and troubling that those type of integrals diverge? So pretty much what it means, the value depends on the size of the network. And that tells you something very important. It tells you that certain things, like average, for example, for this type of networks, when, for example, when gamma is between 2 and 3, they don't make a lot of sense, because average, like when you think about averages, you think about, okay, well, there is this number, and let's say average number of friends is 10, and you think that, well, a lot of people who has maybe 9 friends or 6 friends, and there's some people who has 11 friends, 15 friends, but that's your average. Well, this tells you that fluctuations around averages, which is k squared, if you're gamma in between 2 and 3, can grow. And so by knowing average, you really cannot tell, picking up any other node, you cannot even tell what the value is going to be because fluctuations is much larger than this average. And so you can have, picking up a node, you can encounter a node with like 2 friends or with 50 friends, you don't know. And so average, giving average for that type of network does not tell you anything. It is, again, it is a strange situation. It is quite unusual because, you typically you think, okay, average, and then you kind of, to the left, to the right of average, you kind of know what the network is about. Here, not. Again, we'll spend more time talking about this at the seminars. So you can also look at these networks and kind of approximate or estimate the largest, if the network obeys this distribution, you can actually estimate the largest node degree in the network. Remember, node degree is the number of friends. And the point is, kind of quite obvious that when the network grows, those nodes that have the largest degree, the largest number of friends, will probably also grow in the sense they will get more friends. So the question is, how do they grow with the size of the network? Right? If n increases, how this maximum number of connection increases. And so there is actually a way to show it by looking at the probability of observing a single node with degree greater or equal than the maximum. And you can calculate expected number. And you can calculate, you can just plug into integral and actually take that integral. Now, for example, if the network had an exponential distribution, which is the CE minus lambda k, then the maximum node degree will be connected to the minimum through the logarithm of the number of nodes, which is a very, very weak growth. So your network sort of double, your network increases, 100 times, and your maximum possible node degree in exponential network increases only twice. In a power law network, the largest node degree increases really, really fast. K max is K min times n to this 1 divided by gamma minus 1. So if gamma is equal to 2, maximum node degree grows proportionally to the number of nodes. So that's really sort of emphasize this notion of the winner takes it all. So the largest node degree gets all the connection from the network. And it's getting bigger and bigger and bigger. Now, we're going to talk more about it. It sort of reflects also on this notion that money goes to money, rich gets richer, et cetera, et cetera. So those nodes that have a lot of connections when network growth grow very fast. And those have few connections, they grow much slower. We're going to look at this model next time. But this is a very interesting story that the maximum node degree grows, in particular, depending on the gamma, either grows linearly with a number of overall of nodes, or maybe with some other fraction like square root of n, but it is very, very fast growth. I'll skip this for a second, and just again, talk about this notion of node degree. Typically, when you think about picking up sort of a node, or you want to estimate particular value, you say, okay, here is a random value. I mean, here's the average value, and then everything else leaves plus minus deviation from it, right? Sort of variance. I mean, that's a usual approach. That's why you talk about variance in statistics. And again, in normal networks, variance can be quite small. And that sort of corresponds to this bell shape. But in a power law network, variance can actually be very, very large. Because remember that integral diverges. That really means that in a physical network, it becomes very large. And so picking up a node, average does not tell you anything, because your node degree that you pick up can be average plus minus, huge variance. All right, I see I'm losing you guys with this, but the message is short and simple. Then you hopefully will work through the notes and through the book, and you'll understand this better. But the message is the following. In this type of networks, average doesn't make much sense. because the nodes that you have this very strange distribution with a few nodes that are very high node degree, with majority of the nodes very low degree. And whenever you pick up a random node, it can be very far, the node degree can be very, very far from average. I'll give you an example from the neural network. These are real networks. What you see there is the size of the network. N is the size number of nodes. L is the number of connections. K, average, is an average node degree. And so what you see is, for example, citation network. 450,000 papers, right? 4 million citations. Average number of every citation per paper is 10. But when you look at the actual, distributions, you realize that some papers are actually cited 10,000 times. And some papers cited, once or almost not. But average is 10. So average doesn't tell you anything. And so, there are more of those type of things, right? Or, emails, mobile phone calls, for example. Again, average is 2.5, but, there are people who actually talk, make a lot of calls to a lot of other people. So again, 2.5 is not meaningful here. So the point is, in this type of networks, variance can be very, very large. And because of that, average does not tell you any story. So you have to be very, very careful when you look at these networks and try to say, oh, well, average node degree is this, right? It can be very misleading because node degrees in the network can be all over the place and will be. All right? Okay. Now, I promised, I'm skipping some slides. We have very little time, unfortunately, but I promised you to show, like, these are original, very original papers, 1999, when the first sort of web crawl was done. It's actually, well, Google already existed. Alta Vista existed. There were some other search engines. This was done at IBM. What you see on the left and on the right, these are those histograms in degree and out degree for the web pages, and vertical axis is a number of pages. You see 10 pages, 100, 1,000, 10,000, et cetera, and that's how many web pages have certain node degree, like in degree, which is how many other pages points to it, and out degree to how many pages this page is pointing to. And you notice that, again, with in degree equal to 1, there is, 10 to the 8th pages, but with in degree equal to 100, there are only like, few thousand pages. Again, remember, this is 20 years ago, right? So the web was much, much smaller. But the point is this uneven distribution, right? Okay. And when you look at sort of other graphs, they all pretty much look the same, like internet, science collaborations, and protein network we look at the beginning, it also has this sort of type of distribution. You think you can plot a straight line across this purple dots. Well, sometimes you can, sometimes you cannot. But the big question is, if you have that data, right? I told you that the key parameter, the one you want to use, the one you want to be able to determine, is that gamma. Right? Because we said, okay, this is a power law. Let's say we believe this, but if it's a power law, what's the value of the parameter? In other words, you have your curve, the straight line, what's the slope of the straight line, right? So you need to determine that. How would you do it? That's a question to you. Let's say you have this data. How would you determine the slope of the straight of this? If you think that, if you believe that your model is a straight line, how would you go with the slope? So I mean, well, but what the sort of the very first, the most intuitive thing to do here, the most naive thing.
We can take away our data and make a regression.
For example, I mean, the most sort of, the easiest, right, the most straightforward way to do it is you have this data points, right? You can just try to draw a straight line through this by doing a regression. Now, the trouble with this is, well, first of all, you're not quite sure. I mean, you know, it's clear that there's a straight line somewhere here, sort of, right? But, you know, this doesn't look like a straight line to me at all, right? And over there on the very top, it doesn't look like a straight line. So, yeah, so you probably want to do regression, but maybe like restrict it to a particular part of this graph. It's one thing. Another thing, don't remember that this is a log-log scale. And so your regression will be insanely sensitive to any noise, because when you go back to like original scale, it's going to be, you know, amplified. So regression is what, of course, people started doing at the very beginning. Then they realized it creates a lot of mistakes, and, you know, came up with a few different ways of actually estimating that parameter. One of those through like maximum likelihood. One of those through actually looking at the cumulative distribution function. Now, how many of you remember what cumulative distribution function is? So if the distribution function tells you the probability of, you know, something being within a particular range, then cumulative tells you the probability of this being greater or equal than some value, right? Well, the amazing and surprising thing about this power law distribution, if you take this ck to the power gamma and calculate what's called cumulative, complementary to the cumulative distribution function, which is probability of being greater, then, you know, if you integrate this k minus gamma, well, you actually get k minus gamma minus 1. So it is the same shape, but gamma is, if in the original distribution is gamma, here it's gamma minus 1. But cumulative looks smooth, and you can easily work with it. So that's on the right hand side, right? That further picture is a cumulative distribution function. So one way to deal with this is take your function, you know, do the sort of traditional thing, then calculate cumulative, and then match a line to the cumulative distribution function, calculate the slope there, and then just decrease it by 1. Increase it actually by 1. That's one way. Another way is through maximum likelihood estimation. And this is what you're going to do at the seminar. Okay? One last slide for today that I want to show is this slide. Again, you can hardly see, but the axis here is a gamma, that parameter. And it can take values, you know, any real value, right? Greater than 1. We just discussed that if it is less than 2, then we get problems with average, it diverges. In between gamma between 2 and 3, average does not diverge, but the variance diverges. After above 3, you know, everything works fine. But majority of the graphs that do exist in nature, they actually fit gamma is in between 2 and 3, which is also quite surprising. And that's what's called the scale-free networks. The networks when gamma is in between 2 and 3, when the variance is very large, and average does not tell you anything about scale. And scale in this sense, in this case, meaning number of connections. So I cannot characterize by any particular scale this network, because number of connections varies so much, or mathematically speaking, because the fluctuations are very large. And so that gamma in between 2 and 3, that's what's called scale-free networks. Okay? So that's sort of the summary for today. So we have a power law distribution. You can actually have this distribution. You can, you know, if you believe in your model that no degree is distributed by power law, you can actually estimate the coefficient of the power law, which is gamma. And there is a brute force way by actually looking at this line, right, and just saying, okay, there's a straight line and just calculating the slope. You know, you probably get a lot of mistakes doing this. There is a little bit smarter way by calculating cumulative distribution and mapping a straight line to that. And then there is like the real way is through this maximum likelihood approach, and you're going to talk about this approach at the seminar. All right? Okay. So then that's it for today. You'll have a seminar You'll have a seminar on Tuesday, right? And I think there are 2 sessions running in parallel or something like that that's going to be happening. Any questions? Okay. Oh, good question. I will answer it. I don't know if it's scheduled in the computer room or not. We'll send an email to you guys. If it's not in computer room, you need your laptop. If you want to keep, of course, the work you do, on your laptop, you're welcome to have your laptops. Is it? It's not in computer room. Okay, then have your laptops with you. It's usually helpful. And by the way, try to, if you don't have it, install the Anaconda before, right? Just install it in Network X before when you have, your home Wi-Fi or whatever, when, you're not competing with other people. We'll send out email about this. You have another question? You had a... Gamma, yeah.
But now we said that gamma more than 2, we said the scale 3. But we have average. No?
Yeah, so what I'm saying is, if it is below 2, then, so if it is below 1, like, okay. Let me get back to this. Let me get back to here, right? So gamma has to be greater than 1 for this distribution to exist whatsoever. If it is below, it doesn't exist. Now, it needs to be greater than 2 for average to exist and not diverge. So it has to be greater than 2. Below 2, your average diverges, so anytime network grows, your average grows, everything grows. It's a very unusual regime. Now, but between 2 and 3, your average stabilized, but your variance can grow and diverge. And so that's what does it scale, makes it scale free. When it's above 3, you're again getting into like decent regime of variance being convergent. So. Oh, no, it has to be greater than, it's in between 2 and 3, right? In between 2 and 3. When average is okay, variance diverges. It's above 3 when, everything converges. That's fine. But between 2 and 3, there's this unusual regime where we have very large fluctuations within the system. And fluctuation, I mean, the difference in between the value, the average value, and any value you pick up in the system. We'll get back to this several times with the next lectures, so you will have better feeling. For right now, again, one thing I want you guys to remember is there is this power law, right? There is this power law exponent. There is this gamma coefficient in there. Different networks have different gammas. The interesting regime most of the networks is when gamma is between 2 and 3, right? That's sort of the part where this magic things, strange things happens, right? That's sort of in short. And we're going to go back again in the seminar, we can go back and calculate those, what's diverges, what's not, and how this gamma affects things. Okay? All right. Thank you very much. We're done for today.